So here we are in chapter 2, functions, and you hopefully know quite a bit about functions already, but we're going to go back through some of this stuff, remind you, maybe there's a little something new in here, I don't know, everyone's different. So let's go ahead. So when we talk about functions, as we can see, we have a definition here. A function is a rule. It assigns a output to each permissible input. All the inputs are called the domain, and all the outputs are called the range of the function. So we use function notation. Function notation starts with an f, typically of x. So it's saying this is the function of f of x. And you could also have g of x. You could have h of x. You could have h of t or s of t. So there's a lot of different ways to do function notation. We'll see all of those over the course of time. So let's let f of x be a function that takes any number. Often we call any number the x, doubles it. So you can imagine if we take x and we double it, we're going to multiply it by 2. And then after we do that, we add 1. So this is what it looks like algebraically. If we just think about a number like such as 6 over there on our input side, so look at this little table here. So we have the input of 6. It's saying the function that we're defining here is going to take 6, it's going to double it, and it's going to add 1. So you can kind of think in your head what that's going to look like. And that would be 13. So 6 times 2 plus 1. We can do that to any value that we can put in. And since any value can be doubled and you can add 1 to anything, we can put in any number. So the next input would be -3. If we double it, we get -6. If we add 1, -5. So notice, you won't see this terminology that much, but technically that 13 is called the image of 6, just like the -5 is called the image of -3. But again, you won't see that much. Now, like we already showed there, besides just taking a number and saying, okay, here's this thing I'm going to do to it, it's nice to write it in a shorter way. So algebraically speaking, this is the expression for the output, 2x plus 1. This tells us that we can choose any number for x, and if we do these two operations, we will come out with an output. Besides using it algebraically like that, we like to be a little bit more formal. You'll often see, for example, y equals 2x plus 1. This is often used graphically in a graphic sense. When we graph functions, we often use y. And you'll also see f of x equals, and that's of course the big thing here, is this is your function notation for the function that takes any number, doubles it, and adds 1. So like I said, this is function notation. And as we get into higher level mathematics, we definitely use a lot of function notation. We're dealing with a lot of functions. Now we have find the domain and range. So like we said, domain is all the permissible inputs. So all that means is, if you're looking at a graph like this and you have your x and you have your y's, your domain are anything that you can have for x. That's the domain. Anything that is possible for x. So you can see that this function, it's fairly obvious as you go from, say, -2 to 2, you can see that there's all these y values. But those arrows tell us that this function is just going to keep going up and up and up. And as it goes up and up and up, it's going to widen, 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 meaning that it's going to go all the way from here, all the way to there, meaning that really you can put in any value and you're going to have a y value eventually. Even though it looks like this function with those arrows continues on and on and on and on. In a situation like that, the domain is all real numbers. This is your set notation. Fancy R, as one of my students used to say. You can also use interval notation, since that's what it's said to do. Interval notation is -infinity to infinity. That simply means that there's literally any real number that I can choose. I can plug in, or in this case, look at a graph, and there's going to be a y value for any x value. Even if we can't see it on this little version that we have here, it's still true. So you're basically saying, what are all the x values, the values that go from here to here, this way? What are all the values possible? For the range, you're looking at all the y values. So what are all the outputs? And we can see that for this function, those arrows goes up, up and up and up and up. So those y values, we can talk about everything all the way up. However, we notice that there is a place where the y values start, and that is right here. So this -1 that you see, there is a y value for this graph that is -1. And then there's every value up from -1. But there's nothing below, there's no y values below -1. So -1 is where our range starts. So we put -1. I'm going to close it up because -1 is included. Remember, we do not include -infinity, because they are not real numbers. You cannot say I have infinity shoes. That's not a thing. But it does go up, like I said, up, up, and up, 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 using those arrows. So our range in this case is the -1 to infinity. Other things we can do with functions, and talking about functions, is when using function notation, what's really nice with this notation here is this is saying f of 1. That's how we read that, f of 1. And it's simply saying take 1 and plug it in where you see x. So obviously we get very fast with these. The idea here is that I'm putting in 1 where I see x, and then I'm just evaluating. So the square root of 1 plus 3 is the square root of 4, which is 2. So typically, when you're doing something like f of 1, you are going to get a number as your final answer. Depending on how you're feeling, go ahead and try part B here. It's the same idea. Instead of 1, you have 2x plus 1. But this whole thing is just what goes into your function where you see x. It's the only difference is that instead of 1, now you're putting in 2x plus 1. Trust me. I'm going to come over here due to my video here and my face. But that's the idea here, is that, again, you're welcome to pause if you want. And we've got 2x plus 1. And then we just simplify as much as we can, which might not be a whole lot. So notice we're just adding there. We can't add 2x to anything, but we can add the 1 and the 3. So we get the square root of 2x plus 4. You might be thinking, what else can I do? What else can I do? But there's addition between these two terms. So you can't separate this. This is not 2x plus 4 is not a perfect square. There's no way to write it as a perfect square. And so because of that, we are done with this. We were just plugging it in, and this is our function, f of 2x plus 1. That's it. Now we have something that is so important that I don't even know how to express how important it is. This is what's called the difference quotient. And you will see this in calculus. So if you need calculus, which the vast majority of anyone taking Math 3 does, that's what this is called, the difference quotient. But I want you to realize that it's just algebra. When you get to calculus, you do something with this. But in this course, all you're doing is just doing some algebra here. This is saying take a function, any function, and first plug in x plus h where you see x. Then subtract your original function, f of x, and divide that whole thing by h. And there's a reason that we do this, and you don't learn about it until calculus, but there is a reason, and I'll just tell you that so maybe you can understand that there's a bigger thing involved here that you just don't know yet. But the first thing we need to do is consider f of x plus h. Once we have that, we just write it out and we simplify. So f of x plus h, like I said, is just taking that x and replacing it in your function with x plus h. That's all it is. And you could, if you wanted to, simplify it a little bit first. That is fine. I don't know if you'd rather see this as blue. Ooh, that's not too bad. Okay. But that's the idea. So we'll start with that. And you can do this all in one shot, or you can do it like I'm doing it here separate. but I'm going to get my f of x plus h. You're going to take x plus h, you're going to square it. So you want to get real fast with this. You know the first term is going to be x squared, the last term is going to be h squared, and then you should understand that that middle term is going to be an x times an h plus an x times an h because of the outside and inside getting multiplied together, which is a 2xh. To be a little careful, I need to give myself a little more space there. And then we distribute the 3, and of course we have minus 2. And then what we need to do is set this up. So now all I need to do for my difference quotient is just write out as I see this thing right here. All I gotta do is write it out. So I start with f of x plus h. So you can go ahead and just write that out. We already found it. That's great. Okay, and then we're not done. Okay, we're not done because then we need to subtract our f of x. So don't forget that part. You got to subtract your original function, and that's, we just look, hey, I know what f of x is. It's right there in my face. So we just take that and we subtract it. And then we have our big division sign there, and then we're dividing by h. Now you might be thinking, wow, there's a lot happening here. But don't forget that all it is now simplifying. The biggest thing to remember is that because you're subtracting that function, the signs of your f of x are going to change. So you have x squared plus 3x minus 2. Now, instead, I'm just going to do this. Try to be real careful here. Whoop, whoop, whoop. Okay, so I'm going to change my signs, and that's going to give me a minus x squared, a minus 3x, and a positive 2. But here's the kicker. The great part about this is that now we can simplify. So notice any two terms that are the same, that are being subtracted from each other, opposite signs, are going to be gone. So here we have f of x plus h minus f of x over h. Now we can take x squared and minus an x squared. We can take a 3x and we subtract a 3x. Do you see anything else? We have a minus 2, we have a plus 2. But here's what is so important. You might want to write it down. You got to remember it. What you should see in a case like this is that we have simplified everything we can, and I want you to notice what is left in every term that we have left. So all the terms that we have left that did not get simplified, what is common to all of them? Hopefully you are seeing that it is h. They all have an h. And that is so important because we are trying to simplify this. And I will tell you, because I teach calculus, you're trying to rid yourself of that h that you have in the denominator. And you can do that because you can factor it out of your numerator now because it's in every term that you have. That's the key thing to see. Because it's in every term in the numerator, we can factor that out, and then we can just simplify it. Okay? Now, really, I'm spending a lot of time doing these arrows, but in reality, I'm going to make these equal signs because they are equal. We're just simplifying here. So I did the first one as an arrow, but then I'm going to say, hey, these are equal, and then I'm going to put the next one down here. And now that I've simplified this h, I have 2x plus h plus 3. Okay. And that is actually done. It might sound weird to you or look weird to you, but again, this comes back in calculus, and that's why we're practicing it right now. We'll practice it in some other ways as well with some of the other stuff we do. But you got to know the difference quotient. So if you got to write it in your notes, if you got to put a big star in your notes, star, yes, this is something that you have to know. You have to know how to do the difference quotient. It's going to make your life so much easier when you take calculus. Go ahead and make a note that you want to practice this a lot.